All right, so hello and welcome to this video. And what I'm going to be doing in this video is going through an introduction to modeling with PyTorch. So in particular, looking at constructing a very simple feed-forward neural network for image classification using PyTorch. Before we get started, I did want to show you, so I'm going to pull up an incognito window and go to github.com. And if you search user colon Freem Analytics, all right, there's going to be a predictive modeling repository there. And there's this PyTorch Introduction Jupyter Notebook, and that's what I'm going to be covering today. So you can look at this repository. Again, what I'm going to be working through is a version of this notebook with a couple of the key cells pulled out. So essentially no code there so that we can write that together. And that'll kind of slow me down and hopefully allow me to explain things a little bit more clearly than just simply running this completed notebook. But that's where you can get it. All right, so I've got a copy of that notebook here on my desktop, so this PyTorch Introduction, and we're going to be using MNIST, the MNIST dataset, which is essentially handwritten digits. So if you want a little bit more information about what that looks like, I've also got a video on talking about how we can use dimensionality reduction for predictive modeling on this same playlist on YouTube. So it's a predictive modeling playlist. So you can go look at that. I did at least talk a little bit more about the data set and visualize a couple of instances there so that we could see it. I'm going to kind of not do that visualization piece. I will talk a little bit about the data, but the key thing is our data, and this is all in GitHub as well. I've got this subfolder called data with I've got a feature data set and a target data set. So MNIST underscore features, MNIST underscore target. Both of those are Parquet files. And I'm going to be working from this notebook, so it expects to have that data subfolder in that directory. All right, so let's go ahead and get started. So of course I am using an environment. So I'm using a Conda environment, and I've got polars, NumPy, scikit-learn, a lot of the other kind of things that we always have like matplotlib, seaborn, but also we are going to have PyTorch. So I've got PyTorch installed, and if you haven't installed PyTorch in your environment before, you can just go out. They make it really nice and simple. So you can just go to PyTorch, and you can go to their Get Started. And they've got this nice little widget right here that allows you to figure out, well, if I'm on Mac and I'm using Conda, how can I install it? So some of the options will not be available to you, but you just go to an option that is like this default, and you copy that command. So I'm running Linux, installing from Conda. I do have a GPU, so I can use that CUDA installation. So I have an NVIDIA GPU on this machine, even though I'm not going to use it in this video. Or if you're on a machine that only has a CPU, you don't have an NVIDIA GPU with CUDA, you can install the CPU only. So when you're creating your environment, you would run that installation. This gets PyTorch, Torch Video, or Torch Vision, I'm sorry, and Torch Audio. And those will be things that we're not necessarily using in this video. We'll use in some subsequent videos, but mainly just PyTorch today. All right, so in this notebook, what we're going to do is we're going to look at PyTorch, and what I've actually got in this notebook is an implementation of a very simple neural network for predicting handwritten digits that's written in NumPy. So I went through and did a NumPy implementation. I'll probably post a video up going in that implementation, in higher level of detail. But I've got a NumPy implementation, and then we'll compare that to a PyTorch implementation. All right, so, PyTorch, open source deep learning library. It was originally developed by Facebook's AI Research Lab. And in recent years, it has, it's kind of historically, there's been kind of a couple of players in that space, most notably TensorFlow and PyTorch. So TensorFlow was a Google developed project, I do believe. And of course, PyTorch came out of Facebook's AI Research Lab. They really, one thing, TensorFlow was kind of a little bit, language agnostic, right? And originally I would say, back in the early days of those frameworks, TensorFlow was the state of the art. In recent years, with the data science, AI, ML community kind of really, growing, and I think Python's popularity has kind of led to PyTorch kind of emerging as the clear leader in this space right now. So again, TensorFlow is still very much used. It's a great library. But I think a lot of the new code that we're seeing develop using neural network architectures and neural network models seems to be going to PyTorch first. So maybe that's a sign that that's kind of where things will head. All right, so I'm just going to run a few of these cells. All right, so this is going to read in our data. So I've got feature data. That's that MNIST feature. So each one of these rows corresponds to a single handwritten digit. So the MNIST digits are 28 by 28 pixel images. So if you do that multiplication, you get 784. So each one of these rows corresponds to a single digit, and each one of the columns is essentially the value for one of those pixels in that image, right? So this pixel 1, that's essentially that, the upper left-hand pixel in a 28 by 28 grid. The values can be between 0 and 255. So these are grayscale images where 0 represents white and 255 indicates black. All right, so again, basically we've got for each one of these rows, we know, okay, well, what are the values of the pixels in the image that corresponds to that image? And then we also have our target data, which is the label, right? So it was, okay, well, that one's a 5, or the second row is a 0, and so forth. All right, so we have the features, the pixel values, and what we want to do is use a neural network to use those features as input to correctly predict the targets. All right. All right, so we had 70,000 instances in our data set, and right now the way that we've got, instead of representing this as a picture, we're representing those grayscale pixel values as a 784 dimensional vector that we could use to reconstruct those. All right. The target data right now is just simply a number corresponding to each instance's digit. All right, so what we're going to do is we're going to create 3 data sets from this raw data. We're going to create a training data set, a validation data set, and a testing set. So for each one of those sets, we're going to take that feature data and we're going to scale it so that it's between 0 and 1. And if you think about it now, your pixel values can be between 0 and 255. So all we're going to do is divide the values and the features for each one of those training, validation, and testing sets by 255 to scale it within the interval 0 to 1 inclusive, right? It's shown right there. All right. So how am I going to do this splitting? Well, I'm just going to use a repeated application of scikit-learn's train test split function. All right, so the first thing that I'm going to do is I'm going to define a train test split right here, and I'm going to create a data set called train underscore validation for both my X and my Y's, and then I'm going to create my test set. So basically, here's the way to think about it. I've got 70,000 instances. I'm going to do one split and create a train validation data set. I'm going to hold that over here to the side for a minute, and then I'm going to create my test set. So when I do this, I'm going to say, hey, well, give me 10,000 instances in my test set. All right, so I'm going to go ahead and create that split of my test, get those 10,000 instances aside. That'll leave me with 60,000 in that train validation piece. And then what I'm going to do is I'm just going to pass that train validation data set over to train test split again to create a proper train and then a separate validation set. So again, it's just repeated applications, right? And ultimately what I'm wanting to do is I'm going to use the training and the validation sets to kind of monitor the progress of my neural network's performance as it's learning, and then I'll use the testing as a final evaluation. There is one subtle thing that I want to note about this, and it occurs right here when we're doing that first split, right? So right now, our feature data, if we were to look at it, right? So our feature data shape, we got 70,000 instances by 784. But if we look at our target data, right, we got 7,000 by 1. And why is that? Because our target data here at the end, whoops, let me just do the head of that. Right, it's just a vector. So that first one's a 5, the next one's a 0, then we got a 4, a 1, and so forth, the labels. Well, when we do our neural network model, what we're going to do is we're going to have that last output layer of that neural network is going to have 10 neurons, one representing each one of the possible values for our label, either a 0, a 1, a 2, all the way up to a 9. So I don't necessarily want this data to be represented as such. What I would rather do is do a one-hot encoding where I've got a column for each possible label. So I've got a column for label 0, for label 1, label 2, so forth. And then I use ones or zeros in the column to indicate are the pixel values in our feature data set for that row, which digit do they correspond to? So that's why you see me doing this right here. So when I do this target data to dummies, let's look at that. Target data to dummies. Now I'm just going to do the head. So remember that first one right now, we've got a 5, a 0, 4, 1, and 9. Right? What it does is it breaks it out. And the nice thing about this is since it's using integer values, it breaks it out perfectly, right? So remember we had a 5, so our first row was corresponding to a 5. When we do that split, what this one-hot encoding does, it takes that target data, it breaks it to, I've got 9 possible labels, and that first one corresponds to a 5, right? And then that next one's a 0. Next one's going to be a 4, right? So I'm going 5. We got a label 0 is a 4, 1, 9. Right? And before we do that dummies, right, we see that that's exactly what it was, 50419. All right, so all I'm doing is I'm handing that off here when I do that first split. So my testing data sets, or not my testing data sets, but my Y data sets, they have my labels. If you notice, once, so this is showing the shapes of our training, validation, and test sets. So we got 50,000 observations in our training, 10,000 in our validation, and 10,000 in our test. And if we were to look at Y train, right? So these are, each one of those is going to have the same number of rows as its corresponding X data set, but it's got 10 columns, one for each one of those labels. All right, so now we're going to talk a little bit about the NumPy implementation. Again, I'm not going to go through a tremendous amount of the details here. I am going to post another video that will go through that in a little bit more detail. There's actually quite a few videos out there of people implementing MNIST in NumPy. So again, you can actually, if you don't want to wait for the video, you can go find somebody else. They're usually pretty close, right? And there's of course different ways of doing it. I am going to do just a restart clear all while I've got it at this point. All right, so I've got my data sets, and let's do our NumPy implementation. So what we're going to do is we're going to use a simple feed-forward network. So what I mean by feed-forward network, we just got linear layers of neurons. They're getting in data, and they're essentially applying weights and biases, activation functions, and just pushing those outputs forward through the network. All right, so we're going to have essentially a network with 3 layers. It's going to have an input layer with 784 neurons, right? And one for each one of those pixel values, which we have normalized in this case. We have divided them by 255, so those values are aligned the range of 0 to 1. But we're going to have one neuron accepting an input from each one of those features. All right. It's going to have a single hidden layer of 64 neurons, right? So it's going to take 784 dimensional input, or I guess I should be using this side, reduce that down to a hidden layer of 64 neurons. All right, and then again, we're going to apply an activation function there. We're actually going to apply a sigmoid activation function to each one of those neurons, the outputs of each one of those neurons. And then it's going to pass that along to an output layer with 10 neurons. So we're going to go from 784 to 64 to 10, which each one of those neurons is going to correspond to one of our labels that we want to predict. And then finally, we're going to apply a softmax function at the very end to normalize the outputs of the final layer so that they will sum up to 1, essentially corresponding to a probability distribution. So we'll have those outputs of that last layer. We'll do softmax to normalize, and we will pick the maximum, whichever one of those neurons has the output that's the highest for a particular instance. That will be the label that we predict. All right, so pretty straightforward implementation of a neural net, a pretty simple neural net. So I've just got some parameters here. So our input size, we got 784 layers coming in, 784 neurons in the input layer, 64 neurons in the hidden, and then we're going to 10. Right now, I'm going to use a learning rate of 0.3, and that essentially handles the degree in which we update weights in those between those layers during backpropagation. And then number of epochs is 250. This is essentially how many times we're going to pass over our data set when we're training. All right. So in this case, when we're using NumPy, I'm not going to do any batching. I'm just going to throw everything to it in one batch and say, okay, well, process all, if we're using the training set, process all 50,000 instances at one time and run that through that network. So we'll essentially pass that one big block of data 250 times. All right, and here's the NumPy implementation. Again, I'm not going to go into a huge amount of detail, but I am going to talk through some of the key components of it. So I'm going to use that sigmoid activation function or essentially the activation function on that hidden layer. So this function right here, you give it essentially an X, an array, and this will compute the sigmoid function for those X input values. I've got a function to compute the derivative of a sigmoid function for a given set of inputs, and this will be used during that backpropagation step. I'm using the softmax, and I'm actually using a particular version or variant of that softmax where usually what you would do, the softmax would be if I'm trying to figure out, apply softmax to, I've got a vector of values, say a vector V, and I've got V1, V2, V3 that compose that. The way that you would typically use softmax is you would, okay, if I'm going to apply that to V1, I would say E up to, or E raised to the power of V1 divided by the sum of E raised to the power of V1 plus E raised to the power of V2 plus E raised to the power of V3 and so forth. So you essentially raise all your values using an exponent, and then you divide the individual values. It's like a normalization, but you're using exponents. It can happen that there could be some numerical stability if values, get too big or too small. So one trick that people will use is whenever they're doing any of those computations, that E up to, what they'll do is they'll subtract the maximum value across the entire array. So that's essentially what this modified version is doing. So whenever I'm raising that value, I'm just essentially computing for each one of those. So the key thing is note that X is an array. I compute another array where I'm taking X and I'm subtracting out the maximum value. And then I can return each X value divided by the sum of that. So it's just subtracting out those maximums. All right, so these are just some helpful functions that we need. I set a random seed. I initialize some matrices to hold my weights and biases. So this W1, this would be the weights for the links between the neurons in our input layer and our single hidden layer. Our bias 1 will be applied to inputs essentially coming into our hidden layer. And then W2, that's going to be the weights on the links between neurons in our hidden layer and our output. And then our bias is going to be applied at the output. All right. And then we go through, and actually what I'm doing here to initialize these, this is a particular type of initialization that's referred to as, I think it's a he initialization. Let me do a real quick check. Don't want to get that wrong. All right. So he or chiming initialization. So this is a particular initialization approach typically used when we're dealing with, nonlinear activation functions like a RailU or a sigmoid. So this is just, turns out initialization is quite important in neural networks to kind of make sure that the weights don't, diminish or vanish. So this is a well-studied method for initializing. And then what I'm going to do basically for each one of my epochs, I'm running the for pass through that network. So I first, apply W1 in the bias to my X train, and then run that through the sigmoid at our hidden layer. And then I take the outputs of that and then apply my, second weights, the weights that are between the hidden layer and our outputs, add that second bias and apply the softmax. I'm computing a loss using binary cross entropy. And then I'm also, throughout this code, I'm going to keep track of the loss on our validation set so we can look at how our training or loss is moving on our training set and our validation set. So we go through, we just run everything through the network. I'm computing training and validation loss. And then we do the backpropagation step. So this is essentially computing those gradients. So looking at how that loss varies as a function of our various weights and biases. And then we update our weights and biases using our learning rate. Okay, so this is our NumPy model. What's going to do is this is all going to run. At the very end of this, we're going to have a line plot that shows our training history. So we're going to look at that with both respect to our training and our validation data set. And then finally, at the very end right here, I'm just running our test data through that forward pass and getting those predictions so that we can see the accuracy. All right, so these might take just a few seconds. So actually quite efficient on NumPy. And you might say, well, gosh, it's actually going to be quicker than we see with PyTorch. In this case, which I'm not using the GPU. And you might say, well, gosh, well, why don't we just use NumPy? Well, it's actually quite complicated, right? Because the main thing is figuring out that backward pass or back propagation step correctly, right? Because it involves, you know, the derivatives of your activation functions, and you really got to think about, okay, well, how are those things interacting? And it's quite complicated. And you know, one thing that PyTorch is really, really good at, I mean, this is, you know, kind of what it does is it keeps track of those gradients, and it can do that derivative, that differentiation piece needed for that back propagation very efficiently. Right, so it does save us a lot of mental, you know, stress, because especially in this case, we got just one hidden layer. So this is a simple network. There are image classifiers with, you know, 19 layers, right? And they're using these convolutional filters in the middle. It gets really, really complex. So that's really where PyTorch or TensorFlow, one of those deep learning frameworks, will come into play. Plus, again, we're using tabular data. We got a simple data structure here. I mean, what if we were using images or something else? If we were using images or something else and we had a really, really complex model, we might want to run that on our GPU because it has a lot of, you know, cores that are really good at matrix multiplication. NumPy's not going to necessarily do that. I think there are ways kind of to get around it, but ultimately it would get really complex, be very prone for error. But it can be done, as we can see, because here is the completion of our training step. And we've actually got two data sets here, a training and a validation set. They're just pretty much the loss is progressing exactly the same. And you can see that we get 88% accuracy on that model. All right, if we take a real quick look at where it makes mistakes. So this is, again, just running our test through that forward pass, getting our predictions into a Polish data frame. And we can look at, okay, well, what's the, you know, number of or percent of correct classifications by digits, right? So we tend to do really good with ones. Ones tend to be a pretty easy digit, and zeros. But overall, everybody, we tend to have, you know, above 80% accuracy. That horizontal dashed line, that's essentially a baseline accuracy if you were to just randomly guess, because we got 10 digits. If I didn't show you anything, it said, you know, just guess what this digit is, you'd probably be right 1 out of 10 times. So that's just kind of showing you we did learn quite a bit, even though, you know, we're just using NumPy here. And actually, this is the wrong type of neural network structure for this problem. I would probably use a convolutional neural net, right? Because it's an image problem. And I'll probably post a video in the future that is showing, okay, well, how can we solve this same problem with a convolutional neural net? We probably get a lot more accuracy, you know, and it'd be a lot more efficient. All right, let's see where it makes misclassifications. All right, so this is kind of where it misses. So if I were to look like right here, the lowest one that I see is like those 5s, right? So, you know, the vertical axis is showing what the digit actually was. So when it's actually a 5, and then this horizontal axis, that's showing what we predict. So on the diagonal, this is the cases where the actual is what the predicted value. So 81% of the time we get 5s. Right, so what do we mistake a 5 for? Well, we seem to mistake it for 3s, pretty much everything, right? But really a 3 gives us a lot of problems. And then if we look at 8s, right, it's a similar thing. We mistake those for 3s and 5s, right? But overall, you know, we could train this model for more epochs. If I were to look at this training curve, I mean, it is kind of, you know, starting to, you know, have diminishing returns as far as reducing loss. By adding epochs, but we could perhaps make this better by giving it some more training epochs or more data. But again, I think ultimately it's the architecture that we're using, that feed-forward model, simple single hidden layer, That's the primary limiter, but it does pretty good. Interestingly, if you go watch my video that's posted on dimensionality reduction, we use exactly the same data set, no neural networks. We just use a newer nonlinear dimensionality reduction technique, and we apply this to the data, reduce it from 784 dimensions to 2, and we get about 95% accuracy. So in that case, we actually beat this neural network by quite a bit. But that's not the goal of this video, right? We know this isn't the best structure. What we wanted to do is we want to show how would we take this same network now and put this in PyTorch. All right, so we are going to focus on the PyTorch implementation. All right, so it doesn't look like there's too many cells here, but there is going to be a good little bit of coding involved. I'm going to, try to explain this as best I can as we're going along. There's a few things that are a little bit, most people that have been used to doing, data analytics with like pandas, polars, matplotlib, doing a lot of visualization. There's going to be some things that are kind of core data types in Python that we've never had to interact with that we're going to be, we're going to have to bump up against when we start working with PyTorch. I don't think it's too bad once you, get a little bit of explanation, you understand why those things are needed, but we'll get that constructed and then we will run a model. The model might take a while because PyTorch has a little bit of overhead. With this NumPy implementation, we're dealing with the whole data set as a matrix at one time. So it's actually going to be more efficient than the PyTorch implementation. But again, what PyTorch is going to offer as we get more complex models, it's going to help us make sure that we don't, shoot ourselves in the foot by doing something wrong. Plus, we're going to be able to send it over to the GPU, right? So when we get big data, big models, being able to put that over on the GPU, is a game changer. Even though in this example, we're going to see PyTorch maybe struggles in comparison to NumPy, remember, the goal of this video, I'm not showing a state-of-the-art implementation of a PyTorch model. I'm showing a simple model to help you understand how to construct the models, right? This is probably not the best for this use case. It will work, right? It's going to make predictions, right? It's going to learn something. We've seen the model. If we get it NumPy, it can be 88% accurate, which is not bad. But this is not the best use case of PyTorch. It's just, I think you've got to build from that foundational level, hence why we're starting here. All right, so let's do our imports. So I put the imports for PyTorch separate so we could look at those. So I'm going to import Torch, and I am going to import a module called torch.nn as nn. And these are all just really kind of the standard way that people work with these. And then I'm going to import torch.optim as optim. I'm going to import torch, or I'm going to actually say from torch dot utils dot data. I'm going to import a data set. See, is that coming in? And I'm going to import a data loader. All right, and one thing I'm going to do is I'm going to set Torch's manual seed at 42. All right, so Torch is just, importing PyTorch, and what a lot of times people will do is import specific modules. It really depends. You might say, well, gosh, if we got Torch, don't we already have Torch NN and Torch Optum and Torch Utils? Maybe. It really depends on how the package organizers have set things up, right? So usually there's like an all variable. So I'm not sure even though you've imported Torch, doesn't necessarily mean that you've imported all of these. Even if it does, again, I'm not 100% sure of how that implementation is defined in the init of the package. But I do know it's common we're going to bring in NN as NN and then Optum as Optum. And these two modules, this NN module, what it does is it has essentially building blocks for a neural network, which you would think are like layers, right? Maybe it's layers, activation functions, and things that facilitate building a neural network. And then Optum, that has our optimizers. So we're going to use stochastic gradient descent, but there's a lot of different optimizers, right? Like Atom. I believe Atom is pretty much one of the ones that is, very commonly used nowadays. And that's just a beautiful thing about PyTorch. The way it's designed, you can plug and play and move things around and try things out so easily. Whereas if you were going to go back and do this in NumPy, well, if you're going to try to change your activation function, now you got to figure out how to do the derivative of that. How does that fit into that overall scheme? In PyTorch, literally, you just change the activation function, right? So instead of using an nn.relu, make it an nn.leakyRelu or something like that. So it makes it really nice from a building perspective. All right, so I'm going to define some of the hyperparameters that we are going to use. And right now I'm going to kind of mimic what we've got up above with a few different changes. So I'm going to go all the way back up in my NumPy implementation. All right, now one thing I do want to note before I go too far. So remember we had this learning rate parameter, right? And this is where that learning rate parameter came in. So when we were doing backpropagation, we essentially figured out, well, what's the change in loss with respect to our, that W2 array, our B2 array, W1, B1, our weights and biases. And then what we do is we say, okay, well, update our weights, essentially subtracting from them that gradient times our learning rate. So as our learning rate got big, we would make bigger changes, right? So we would, if learning rate was 1, we would just be subtracting that gradient for W2 or that gradient for B2. That learning rate being a fractional value essentially makes sure that we don't make too big of a change at any given time. So it allows for a more controlled, conservative kind of learning process. Could prevent overfitting. One thing that's different though is like, in our NumPy implementation, we were giving it all the data. So it had all the information at each step. So I'm going to change that learning rate just a little bit in our PyTorch implementation because I'm going to show you how to batch it. Not necessarily that we need to batch this data because it is pretty small, right? I mean, you might say, well, gosh, it's 784 features and there's tens of thousands. Yeah, but from a computer's perspective, it can store that fairly efficiently. So when I say small, it's small from a memory standpoint. So we don't really have to batch it. Now, if we were dealing with large images, text, and we're trying to run things on the GPU where usually memory is limited, yeah, we're going to have to batch. So instead of showing you an example where we don't batch, I'm just going to go ahead and show you an example where we do batch. Right, so instead of that learning rate, I'm going to move that down quite significantly, 0.1. And typically you actually see learning rates quite a bit lower than this, right? So I would typically see something like 0.001 or 0.0001. There's some interactions with the types of activation functions you're using and other things, but so that is one of those parameters you kind of need to think about. Okay, well, let me try some different variations, but we're just going to do a conservative learning rate right now. And I'm going to put one additional parameter, which is going to be a batch size, which is going to dictate, instead of us providing all of our examples in each, in one go, right? What we're going to do is we're going to provide it in batches of 32. All right, so this 32 is kind of coming from the GPU line. So usually when you are running things on the GPU, you want your batch size to be kind of in a multiple of 8, I believe, 8 or 16. Usually you'll see a 16 or 8 and sometimes 32, but it really depends on your memory and the size of your individual data pieces, right? So if you're sending really big images, you might have to send batches of 8 if you have a low memory GPU, because when you run it on the GPU, you've got to send your model. It has to actually be instantiated on the GPU. You can't have the model on the GPU and then sending data. You've got to send it to that device, which is not something I'm going to cover in this video, but we will in future videos. But if you're running on the GPU, you got to send the model to the GPU. So if your model's already large, like some of these language models or some of these image classification models get really big, it might be that you can't even fit the model on your GPU. But if you can, you might have very little remaining memory, and you use that batch size to control, okay, trying to make sure that I'm not running that GPU out of memory. So that's where it becomes important. And it is, there are not many cases where you can just say, what, send all of my data to it. We'll be good, right? So we're going to send batches of 32, and we're going to make 250 passes over the entire data set. Right, so the way the code works, we're going to send for each epoch, we're going to iterate over the data, sending it in batches of 32, running it through the forward pass, updating the weights through backpropagation. And then once we finish, we're going to run another epoch, right? So in this case, it's going to be essentially however big your data set is divided by 32. the ceiling of that, times 250 is essentially how many passes through and weight updates we're going to get. All right, so what we're going to do to facilitate this batching is we're going to want to use a Python object called a Dataloader. All right, so we're going to use this thing called a Dataloader. We imported it here, but actually to use the Dataloader, we have to define a data set. Okay, so we essentially have to define a data set structure, and then we can hand that off to Dataloader, and it will give us back this object that will be used to generate batches of objects going into our neural network. All right, so let's look at doing that, right? And again, I'm kind of going to fly through a few things. There's a few additional things that we will. Well, let's go ahead and let's look at one real quick that you're going to notice. So when we're looking in Torch, right, the key kind of data type that we're working with in Torch are these things called tensors. All right, so it's almost analogous to a NumPy array, right? So if I say, well, this is my tensor, right? I can, grab things, right? I can index this out, but if I look at the type of this thing, it is going to be a PyTorch tensor, right? So in PyTorch, you're going to be working with tensors, right? This is going to be, and this is true for TensorFlow, hence the name TensorFlow. You can actually, if you had a NumPy array, right? So I could say, well, my NumPy array, NP array, let's just say 1, 2, 3, right? So that's a NumPy array. I believe you can just do a torch tensor and you can just hand it off that array. So we'll say a torch dot tensor. Right, hand off that array. And then there you go. So you can move between those. And they have a lot of similarity in the methods that are defined, but they are not the same thing, right? Let me just take another look real quick at this tensor. So if I do my tensor, let's see if we do D types. All right, so let's do a D type. There we go. So in this case, it's a torch tensor of 32-bit integers. Most of the time we deal with floating point tensors. So I'm just going to put a dot at the end of each one of those numbers. All right, now this is important. This is extremely important. So let's look at NumPy. So if I do my array and I say, well, it's going to be a NumPy array. I do that 1, 2, 3. All right. So if I do my array and then do D type. All right. So really subtle thing. A lot of time you're going to be working with NumPy and you might have some NumPy data and you're going to create a torch tensor from this, right? Notice what happened when I created a tensor using just raw data, 1, 2, 3. What did it return? It returned a tensor with D type float 32. So a 32-bit floating point number. When you do the same thing with NumPy, what does it do? It returns a NumPy array with data types float 64. So instead of using a 32-bit, it uses a 64-bit float. Now watch what happens if I do a torch tensor from my array. Right? Notice it's float 64. This is one thing that's really subtle. It burns a lot of people or gives them a lot of errors early on, makes it a little bit difficult. By default, PyTorch uses 32-bit floating or 32-bit floating point numbers, right? And it does that because it's less storage space to store a 32-bit float than a 64-bit, right? Because one takes 32 bits, one takes 64 bits. So to conserve space, they have kind of got behind this default of 32. But if you're coming from NumPy, a lot of times you'll do 64 bits. So the interesting thing is like you might get your data and prepare it and convert it from a NumPy array to a tensor. Well, if you're not careful, it's going to do that as a 64-bit. And then when you're in your neural network and it's looking at its weights, those will be 32s. And actually, it's going to complain and give you an error. It's going to say, oh, I don't want to operate with these 32 and 64. You need to convert them to a similar type. And that's going to be, we'll actually demonstrate that error just so you'll see exactly what it looks like. But that's one thing to notice. In PyTorch, we're working with a tensor, which we can build from NumPy, but you got to be careful to make sure. So how would you change that? Well, I could cast, or I could say as type np.float 32. Now that thing's a float 32. And notice when I do this now, that's just a regular tensor. So notice that difference. When I take away that and create my array, it's a float 64. And PyTorch is saying, hey, I've got this tensor, and it feels the need to give me this extra information that's 64 bits. Whereas when I do it here, it just says, hey, that's normal. All right, so that's one thing to kind of note. But ultimately, we're going to be dealing with tensors, and we need a data set. So what we actually have to do is define a class. All right, and this is one thing that was a little bit painful for me because I don't use classes a lot. I mean, I know their use cases and I know their value. Just not something I use a tremendous amount, right? But in PyTorch, we are going to have to use classes. And they're not that bad. I'm going to kind of show you a couple of recipes and you can kind of use these. You will need a class that inherits from that dataset class, which we imported. So this will import some, important methods and properties from that we don't have to define. And we're going to need three things in our class. So first off, we're going to have to define an init method, right, which will tell us what we should expect. All right, so whenever we're working with a class and we have a method, the first argument should be self. So the class's instance. All right, and what I'm going to do is I'm going to pass a data array, which is going to be our feature data, and then a label array, which is going to be essentially our one-hot encoded label data. And then what I'm going to do is I'm going to create some attributes on this class called data array. All right, so whatever I pass in, so when I instantiate this class, I need to pass it a data array and a label array. You don't have to pass it self. That's just basically pointing back to that instance of the class. And then I'll need to pass it my label array. And I'm going to create attributes on the class called self data and label. So if I create a data set, there will be a data attribute and a labels attribute that I can look at. So we need an init method. All right, and in our case, or in all cases, you need another method called length or len. So this allows what this has to do is tell each one of your data sets needs, of course, you got to define the things to actually get the data in. That's what we've done with our init method, where we need our data and our labels. Then you have to define this length, which should basically allow PyTorch to figure out how long is your data set, right? So this will vary. Right? In our case, well, we have this data array. Okay, I've saved it as data. So assuming that I pass all of my feature data to it, right? So let's think about this, right? If I've got X train, right? So this is going to be my data array, or I could got, Y train. That's my label array, right? If I wanted to tell, if PyTorch needed a way to figure out how long it is, well, this is a NumPy array. I can just take the length of that, right? Well, it's 50,000. Well, that's going to be what we return. So we got to tell PyTorch, hey, the way that you figure out the length of this thing that I've handed you is you'll get the length of, in this case, self data, right? Because when I initialized it, I said, hey, create this data attribute, right? And it's going to be the data array. Notice that that's passed in the initialization. So when we're doing length, all it knows is, hey, I've got this instance of myself, and I have a data attribute, which was defined in my init. So I want to take the length of whatever's stored in self.data. All right. And then I'm going to say def. You've also, in addition to length, you also have to tell it how it can get items. So what do you want returned when you grab an item of this data set? And that's going to be a get item method. I'm going to say it's going to take in self, and it needs to take in an index. All right, and I think this is the recipe you've got to use, right? So returning self, how do I figure out how long I am? And if I had an index value, how can I use that index value to get essentially instances of your data, or in this case, our data and our labels that we want back from our data set. And we'll see this all come together very quickly. So what I'm going to do is I'm going to say, well, data row is going to equal to self.data, because remember, this is what I'm going to pass in. You need to think about what am I going to hand off. So this is going to be my data array. Well, if I want to grab index position 1, that'll do it. All right, so you give me an index, and I can grab that. So that's what we want PyTorch to know. So I'm going to say self.data for my index. And for now, I'm going to go ahead and put a comment, and I'm going to say as type, because that was a NumPy array. And remember, we know that this is going to be a problem. So when it's handing these values back, it's going to try to convert those to PyTorch tensors. So I know that that's going to be a problem, because by default, if I look at xtrain and do a dtype, that's a float 64. All right, so I know I'm going to need to do this, but we're going to let it fail first. So I'm going to get a data row, and then I'm going to say a label row. Label row is going to be self.labels. That. And then I'm going to go ahead and copy that down as well. And then I'm going to return data row and label row. See if that runs. Fantastic. Great. All right, so now we can use this to create some various data sets. And I've actually got this code over here. Instead of writing all of this, I'm going to write one of them, and then we'll copy it for the others. How about that? All right, so now we've got this MNIST dataset class. So if we wanted to create a train data set, what I can do is I'm going to instantiate a version of that class. It takes a data array and a label array argument. So my data array, in this case, since I'm looking at xtrain, or I'm looking at my training, I'm going to provide it xtrain. And then my label array is going to be ytrain. Both of those are NumPy arrays. Right? So now if I look at the type of this thing, all right, it's an MNIST dataset class. It should have attributes on it. So if I look at train dataset dot, I've got a data attribute, right, which we defined. That's just the data array that we passed in. And then I've got a labels attribute. All right. But more importantly, now that I have a data set, I can make a data loader. So I can say train data loader equals data loader. And what do we have to give it? We can give it a data set. I usually will give it the data set, the batch size, and this shuffle option. So I'm going to say data set equals our train data set. We'll say batch size equals whatever that we've got stored up here in batch size. And then shuffle equals true. Perfect. Now, just to show you this, now I've got this data loader. What if I said, well, for batch in that data loader, and I'm just going to break immediately. All right. So what this is doing is it's passing out a batch. So we can now iterate over this thing, and notice it's returning. In this case, let's look at, the length of that batch. Right? It gave me back two things. Well, what's the first thing in that batch? Well, I don't know, but if I look at the shape of it, well, it's 32. So it gave me a batch of 32 rows by 784. So it's giving me back a batch of feature data. And if I look at attribute or that item 1, well, it's giving me back a batch of labels. And we defined it that way, right? So it's grabbing, data rows and label rows, and it gives it back in a batch. All right, so that's what those data loaders do. So now we can iterate over this in a batched fashion. All right, so a better way to do this would be, for feature data, maybe batch feature, batch labels, right? Now our batch feature data, we can see that at the end, right? That's going to be a torch tensor, size 32 by 784, and if we did our labels, right? Key thing is this. Let's grab that batch feature data. Notice it's a float 64. That's going to bite us here in a minute. Again, it's a really subtle thing, but it can cause people a lot of headache. All right, so I'm going to go ahead and do the same thing for our testing and validation sets. And I'm just going to copy this over instead of doing that to kind of speed us up just a little bit. So I already had that code prepared. So I've got our validation data set, validation data loader, test data set, test data loader. Great. All right, so we've got our data loader. And we've looked kind of at the shapes of the things and the types of the things that are returned. And now we need to define our neural network structure. And again, we are going to need to use a class. I don't think you have to do it this way, but I would recommend you doing it this way because it offers some nice characteristics or features that we can use later on. So we're going to use another class. And what I'm going to do is I'm going to make a class called a feedforward neural network. And this needs to inherit from NN module. All right, so again, we're passing it a class, and basically that's allowing it to kind of prototype itself off of that class. That's the way to think about it. The way that we typically do, and again, these are recipes, right? So you can kind of come back in and modify both the data set depending on what your data is. You just need to think through how do I get get an item or get the length, and what do I need to pass in? And then similarly on your network, you've got to define a few things. So first off, we need to define another init method. All right, it's going to take in self. We'll give it our input size. We're going to give it our hidden size. And we'll give it our output size. That should be good. All right, now one thing that I am going to do is we're going to use this super method. So I think this allows you to refer to the class by its name within the function. Could be entirely wrong about that, but this is very common for defining these neural network classes within PyTorch. So we'll say super, and really the thing is you just do super of the class name. Just pass itself, and you call init on that. All right, so again, that's the recipe. Again, I'm a little bit fuzzy. Let's see, what does... Let's see if I can find... Yeah, so it's used to call a method from the parent class. All right, so it allows you, in this case, it calls... okay, so what it's doing is it's... So the parent class in this case is NN module. So by running this, it essentially calls the init method of NN module, and there must be some things that get initialized there. So what this super is doing is it's saying, hey, well, when I define FFNN, I'm essentially saying that this is built off of a parent class called NN module. And when you do the super, it goes ahead and executes that init statement. And there's probably some nice magic that goes on when you do that. All right, so that's what we do. And what we have to do is now define our neural network structure. So I'm going to say self. I'm going to make a fully connected layer 1. That's going to be our first one. This is going to be a linear layer. So in NN, we have a lot of different layers. It takes in features and out features. So we're going to give it our input size. And remember, our first layer is going to go from 784 to our hidden layer size. So we're going to say that's going to be our hidden size. All right, then we're going to define our activation function following that. So I'm going to call this AC or just A1. And that is going to be a sigmoid activation function. All right. And then I'll say self dot our next fully connected layer is going to be another NN linear. Linear. Very good. And remember, this would be essentially the fully connected layer. So the input size, let's look, input size, and then the output size here. So our input size is going to be essentially that hidden size. So we're essentially looking at that linear layer right there in the middle. right? So yeah, this is our input layer. Maybe I could have called that input. This is actually our hidden layer. And this is these two right here, the input and the hidden. That's essentially defining the weight matrix between the two. Our hidden size, and then it will go to output size. That'll be that weight matrix. And then finally, we're going to have a softmax function, which is going to be an nn.softmax. And it requires you to tell it which dimension are you going to do the softmax all across. In this case, right, so it takes a dim. And in this case, we'll say dim1. All right, so we're going to pass things into our fully connected layer. Then our activation function will get applied. We go through that next fully connected layer. Essentially the weights. I think these were really helpful in defining the weights. And then we go to that softmax. What I'm going to do is I'm going to say, hey, I want the weights initialized. All right, so there's different initialization functions in here. Right, you can do Xavier or this Chi-Ming, and we're going to actually use this Chi-Ming normal. All right, and we're going to apply that initialization to the weights from that FC1, because remember it's from our input to our hidden size, so this is the weights in between that input layer and our hidden layer. So the way that we do those initializations is such, we pass it the weights from that layer. That's how we do that. So FC1 weight. And then we'll do the same thing for our other weights. FC2 weights. All right, so this essentially is just building the pieces of our model. It's not telling us how they fit together. So usually when you're writing these Python or PyTorch classes, you're going to have your init function. Of course, call that super. That allows you to go ahead and inherit from nn module. You'll define the various building blocks. So we've got a linear layers, sigmoid activation, another linear layer. And again, those are really defining the weights. And then that softmax. And then you need to define a forward pass. All right, it takes self, and then we'll just give it some input, right, x. That's what that's representing. So if I call this model with some input x, this is basically going to say, what do we do with x? All right, so we're going to generate an output of our first hidden layer. So we'll say self fc1 x. So we're going to pass x, lowercase x here, into our first fully connected layer. So going for those, essentially that weights parameter, right? So it's going to go through and be multiplied by that weight matrix, which is input size by hidden size. We're going to save that in out. And then what we're going to do is we're going to pass that output to our activation function. And this is kind of the way you do it, right? So we initially pass in x. We say, well, the first out is, going through our input layer. Whatever that output is passed into our activation layer. It gives an output. We're going to pass that to our fully connected layer. And then we'll pass that output to our softmax. All right, so this output will go to our fully connected layer here. And then to our softmax. All right, and what we're going to return is that final output. And that is it. All right. Now, the beautiful thing about this is, what if I wanted to do ReLU activation? Well, instead of doing that sigmoid, I could just say, well, let's do a ReLU. I can do a ReLU right there. What if I want to do a leaky ReLU? Let's see, is there a leaky? There it is, leaky ReLU. So you can change those things so easily. Adding new layers, you just got to think through, right? Because we're getting input, we're going to hidden size, then we got to go to hidden size to output. So you got to just kind of think through that just a little bit. But this is where PyTorch makes things a lot easier. All right. So we're going to do a quick bit of testing on this neural network model. So we'll get just a very basic implementation of it up and going. And then we'll see it's going to have an error because we have to go back and fix this. Then we'll go add a few more bells and whistles, and I'll have to pause because it'll take a minute to run, and then we'll be done. We'll assess its performance. All right, so the first thing I'm going to do is I'm going to instantiate a version of that FFNN class right here. Right, remember, what did it take in? It took in input size, hidden size, and output size. All right, so let's just get those down as different arguments. And I'm actually going to assign them to the value. So input, hidden, and output. Great. So we named them the same thing. So we say equals input size equals hidden size, and then equals output size. All right, so this instantiates a version of our model, and that ran. All right, what we have to do is we have to tell it what our criterion is for computing loss. All right, so we're going to say criterion. Right, so here's our model. We've defined our forward pass and our layers. Now we need to tell it, hey, when you get these outputs, what are you going to compute the loss as? And that's all built in that NN. So in our NumPy implementation, we use binary cross entropy, and where that is in that NN module is cross entropy loss. And there's other types of loss, and this is again what makes it really beautiful with PyTorch. We had to figure out the equation with NumPy and then figure out how to differentiate. But in, with PyTorch, we just, okay, I want to choose a new loss. We'll just go through and, find it in NN and, make sure it's valid for your problem. So we need a criterion, and then we need an optimizer. All right, and that is located in that optim module. So again, there's things like, atom, attograd, a lot of different optimizers. We're just going to use stochastic gradient descent. And it has a few parameters, so you need to pass it parameters. And where are those parameters? What are those? Well, you actually just give it your model. Models have a parameters method. We'll look at that here in just a second. All right, let's just look at what that is, because we've already instantiated it, I believe. All right, so this is just, some generator. Let's see if I can do a list here. This might be a bad idea, so I'm going to just grab 0. Yes, this is one of our tensors, your weights, right? So you're just handing that to your optimizer. Right, so this is probably that first weight matrix. Let's just look. Let's do a shape on that. Yeah, so that's that's 64 by 784. That's that first weight matrix. So it's just handing that off to the optimizer, saying these are the things I want you to change. Your bias parameters are in there, your second weight matrix, and so forth. And then you can give it a learning rate. And I believe it is just, LR. And by default, see, they keep that at a fairly small value. So we've got that saved in learning rate. Great. All right, and then we're going to go through and we are going to do our very simple training steps. So this is the way it would be. So you say for epoch in this case, we're going to say range epochs. All right. And what we'll do is we're going to do a model.train. One thing that is very important, and you'll see this when we write that full bore version of the code, is you can run models in training mode or evaluation mode. Because one thing that PyTorch is doing on those tensor objects, it's storing the gradients. And you got to be really careful about that. This is, again, the beautiful thing that PyTorch is doing for you is keeping track of those gradients. It knows how to do that differentiation. But you got to be really careful that you don't run things like maybe when you're trying to evaluate something and you don't change those gradients. So you can explicitly say, hey, I'm running it in training mode right now. Or you can say I'm running it in eval mode. And you're going to see there's actually an extra step that we do right before we run the backward pass, right? Because all we've defined right now is our forward pass. PyTorch is going to figure out the backward pass. But what we're going to do is we're going to tell PyTorch every time before we run that backward task or backward pass, zero out the gradients, right? So because it actually will keep track of them over time, and if you don't zero them out, the gradients will just cumulatively add up, and the model won't be converging well because it's got information from previous batches in there. All right, so what we're going to do is I'm going to say, well, we're going to be model this in training mode, and I'm going to start keeping track of this running loss. I'm going to say that's going to be 0.0, and then I'm going to say for rows labels in our training data loader. All right, so I'm just going to run that through, and I think we did that without that. So again, remember we made those data loaders. It gave us back a batch of data, feature data, a batch of labels. what we do is we get our outputs by passing that to our model. All right, we just pass in our rows, our x's, and then we compute our loss based on whatever our criterion is, giving it the outputs from our model and our actual label. So you can see at this point, right, we just really need to think at a high level what's going on. Once you build that data set, once you build that model, it's going to handle that differentiation, all of that. Whereas up here in NumPy, right, we had to really be very specific exactly what's going on at each step. It worked, but it could be very prone to error, right? It's easy to make a mistake. So we give it our outputs, we compute a loss, and then right here, what we do is we say optimizer dot zero grad. So this will zero out those gradients for us, make sure we're not computing or keeping old gradients. And then we'll say, hey, based on our loss, so it's going to essentially do that optimization. And then we're going to say, okay, well, based on our loss, we want to do a backward pass. So this is going to go through and compute those gradients. So we zero out the gradients, we use our computed loss, we call this .backward method that executes that backward pass, back propagation, and then based on those computed gradients, our optimizer, which in this case is binary cross entropy, will take a step. Really interesting, right? So if you think about this, we've defined our decision model, that's that neural network structure. We pass data through it, we compute the loss, and then PyTorch, all of this is all it needs for the back propagation. Again, assuming you got your model defined correctly. You just say, hey, forget all the previous gradients, do that back propagation thing, and then find that, that gradient, that region or, direction of steepest descent in loss and move that direction. All right. And then finally, what we're going to do is we're going to do that running loss. Right now, that loss, that's going to be a tensor. Everything in this model is going to be a PyTorch tensor. And we'll just get .item, which gets the value of that. Okay, and then we're going to go ahead and compute a training loss right here, which is going to be equal, because here's the key thing. Notice that we're running through, we're adding this loss for each batch, right? So in this case, we're batching in steps of 32, so that loss is going to be based on those 32. So that's not the loss of that whole epoch, right? Because you got multiple batches of 32. So that's why we're doing this training loss. And what we'll do, we're just going to add, each time we get a new batch of 32, we're adding that loss for that batch of 32 to it. And then at the very end, we're going to take that and we're going to divide that by the length of our training data set. So we'll just say the length of our train data loader. And I'm going to put just a little bit of machinery in here to keep track of that. So we'll say this is going to be our PyTorch training history. Make that a list. And then at the very end, I'm just going to say PyTorch training history dot append. All right. And we'll put in the epoch, which I'm going to say that's going to be epoch plus 1 because we're using a range that's starting from 0. I'm going to right now just say the data set because we'll come back and do the validation. So we'll go ahead and say that that's going to be the training set. And then we'll do our loss is going to be our training loss. All right, so let's do some testing with this just to see if this is working. All right, we should get an error pretty quick. All right, so here we go. Right, and this is where it gets a little bit complicated. So you've just spent all this time, you've been digging around, it's taken you days or hours, you've got your first PyTorch model. It's supposed to be really good and easy. And all of a sudden you're confronted with red. Right, so when you're calling your model, you got this weird traceback error going back to that fully connected layer 1. And then here's the interesting thing. The error you get back is not very informative. So it says matrix 1 or map 1 and map 2 must have the same D type but got double and float. What's a double? All right, we don't have that. We were just looking at float 64s versus 32s, right? So this is kind of giving you a hint. PyTorch is probably using a language like C or C++ under the hood, where double and float, they're both floating point numbers with different precision, right? So different floating point bits, right? And really what this should be saying is saying, hey, I expected a 32-bit float, but I got a 64, right? But again, the error is a little bit ambiguous, but you just go up here. Remember when we defined our data set, when we had those, this was grabbing those rows of that NumPy array, change that to where it cast it to a float 32, rerun that, run everything going down. And for now, I'm just going to do a few batches. All right, let's just do, instead of epochs, let's just do 10. All right, let's look what we've got here. So let's see, where do we go? So now we're good. It's saying cross entropy lost argument input must be a tensor, not a NumPy array. So let me just do a real quick double check. So we should be getting labels. Let's look at labels right here. Labels. And that is a tensor. Let's just say D type. Yeah, labels dot D type. So that is a 32-bit argument input. Let me just double check, make sure I haven't done anything. Cross entropy loss, that looks good. Optimum learning rate. Let me just go back up here to my data set and make sure everything is in order here. As type MP float. So I've got that guy. If I look at my data set, when I do this batch, I've got batch feature data, which is a tensor. I've got batch labels. And if I grab one of those, right, what is the D type? So that is a 32-bit tensor. Let's make sure we've got nothing in here that looks awry. Again, just double checking everything. Input hidden, hidden output, dim is equal to 1, FC weight, X, all that looks, here's the deal. So I'm returning output, right? So apparently, let's think through how this is working. So I've defined out right here. So I give it X and I use out, but I return this thing called output. So what's going on is when I go through here and pass it labels, yeah, I'm not sure exactly what's being passed back on this forward pass. So I need to be passing out here. That's, I'm wondering if output is clearly defined. Yeah, and it's a NumPy array. So that must have been for my earlier NumPy implementation, but that's actually where the error is, because this is saying, hey, I need a tensor, but I'm getting an array. And that's why I was going back and kind of looking at where I could be, sending an array out. And this is the step right here. There we go. So that's running. I'm going to give it a second and pause. All right, so it looks like the model ran, which is great. So we're going to look at what I'm actually going to do is do a kernel restart clear all. So we're going to run the, I'm actually going to skip the NumPy. Well, we'll run it again actually. So let's go ahead. I'm just going to run everything down clean. So we'll get that NumPy implementation going. We'll get down to our PyTorch implementation. So the key things that I really wanted to show you is this use of the Dataset Dataloader and how do you define that model class. All right, so we defined our dataset class for the MNIST data, and then we used that data loader. We saw, looked at how we can get batches out, and we defined our neural network model, that class. All right, we saw how we need to make sure, very careful, that we're using 32-bit floating point numbers if we're dealing with NumPy arrays, which a lot of times we will be if we're coming from pandas or polars or something else. And then make sure you pass the right thing to the return statement. All right, so here is our basic model just to make sure that everything's going on. We instantiate the model, come up with our criterion for computing loss, figure out an optimizer, and then you code up that training loop. All right, what I'm actually going to do is I'm going to bring in a more elaborate version of that, and I'm going to let that thing run. I'll talk through kind of the key changes here. All right, so this was the training loop that is actually on that notebook online. So it's a little bit more elaborate. I do have a flag. If you can, if you want to retrain, you can set that to true or false. So here's that model instantiation. One thing I did want to show right now, if you look at this folder, we don't have any weights. Well, these models can be quite complex. And even though, again, this is a simple model, it actually takes a little bit of time to run because I'm running on the CPU and whatnot. So what you probably want to do is train it, save that model, and then you can instantiate it later using the weights from your last training run. So I'm just creating a pathlib object, and basically I say, hey, if this flag is set to true or that model weights doesn't exist, then we define our model, go through doing that forward and backward pass. I do that for both the training pass, and then I'll also do it for a validation pass. Now here's a key difference. Remember when we were doing our training, I said model.train, and I did the outputs, computed the loss, and I had to do that optimizer, zero the gradients, do that back propagation step, and then update the optimizer. When I'm doing validation, I'm not changing gradients. I just want to see how it performed. So the key thing is when you're running it, I'm setting that model in eval mode, and then I'm using this with statement to say, hey, no gradient should be changed during this part right here. So both of those things you'll want to do. So set the model to eval mode, and that essentially changes the way that some layers are kind of computed. So both of these things actually don't do the same thing. You need them both. And then this is kind of saying, hey, don't do any updates to gradients. Just take the rows in my validation data, pass that off, get the outputs, compute the loss, and then adding that to our training history. After this thing has went through all of its epochs, I save the model. This is how you do that. You save the model's state dict. That's essentially its weights. And I'm going to save it to that model weights path, but I'm passing that as a string argument because I don't think it works with the pathlib object. Then this will plot the training history for that run. All right. Now, if this statement right here failed, so if that evaluated to false, so if train PyTorch model is false and that model weights path exists, you'll go right here, and this is how you would load that model. Here's the key thing. Model has to be an instantiated object. What do I mean by that? Well, if I look up here, regardless of if you do that if or else, I've created model. It's an instance of that FFNN class with a certain input size, hidden size, and output size. It's not going to read those weights in and say, oh, well, this is the type of model you built. No, you have to instantiate. You say, hey, here's my model. And then instead of training, it'll just say, hey, load the weights from this file path, right? And then finally, at the very end, this will do some evaluation. I'll actually show that real quick in another step, and then we will go from there. All right, so I'm going to run this. I will pause it one more time so you can see the whole thing. So at the end of this, it's actually going to save that model state dict in an area called MNIST model. We don't see that here now. And then when it does that training, it's going to save the progress in a PNG file called PyTorch_training progress. So I'm going to let that start up. Pause it for just a second. All right, so the model just finished up. Here's our nice plot for the training progress on both our training and validation sets. And again, you might bring this down and run it, even though I've got that manual seed. There's a lot of sources of randomization in this notebook. So I've ran this a few times and it comes out maybe just a little bit different. But overall on this run, right, we see pretty nice progress on both the training and validation sets. We actually get an accuracy of 93.58, even though we are using exactly the same model architecture as we did with the NumPy implementation. Same, sizes of input, hidden layer, and output layer, same activation functions, softmax. Again, it's just the way that these things behave and do that random number generation. And there's actually some interesting things in the way that the optimizer uses that learning rate. Because if you remember earlier, we had a much higher learning rate. We were using like a 0.3. when we were using NumPy. I can scroll up real quick. Right, so we use like a 0.3, and that turned out well with our NumPy implementation. I think that's because we weren't batching things, right? We were sending a lot of the whole data each time, so we use those much bigger updates. But when we're batching it, we're making many more smaller updates, so that we have to change that scale. But overall, it does well. If you look over here, we've got our MNIST model.pth, so we can load that thing up. And then we've got our training progress plot in case you wanted to look at that in detail. So the next time that you were to run this, I'm just going to do a kernel restart, clear all outputs. All right, so if I were to go back up to the top, go down. All right, so our NumPy implementation, we'll just go ahead and skip that for now. I'm just going to set that to false. Don't want to run it. It's about 88%. Yeah, I guess I'm going to have to run it. So I'm going to run my NumPy implementation. All right, let me just go ahead and kill it, restart it, run it all again. So my numbers are nice and consecutive. All right. Should have thought through that. All right, so we'll run that. We'll go ahead and do the performance assessment. So if you set that to false, you don't need to run the NumPy performance assessment. All right, so this time we're going to go through, define the models. All right, so I keep that train PyTorch it's set to false. So I've got that model file path. So this time it will not train. And the plot is only generated when it trains. So that's why I saved it. So this time it's going to hit the else condition. We've got model instantiated above right here. And so this time it's just going to load those weights from that state dict, and we should get roughly the same accuracy, which I think was about 93%. So we'll give that a shot. NumPy should finish up here shortly. Just did. So now we've got our saved model. All right, so I just was putting it in evaluation mode. Now, I did want to show you, like in this case, when I'm evaluating it, I'm saying, okay, well, I'm putting in evaluation mode. I'm getting the correct and the total. I'm doing that torch no grad thing, so we're not computing gradients. And then I'm using that test data loader, and I'm going over batches. So I'm getting rows, labels, and I'm essentially computing the outputs. And then that output is going to be a soft max. So if I were to look at the value of output right now, right, so outputs is right here. If I look at that, that's that soft max output, right? So each one of these, if I were to look at output 0, right, so that is a tensor, right? And it has 10 dimensions, one for each of our outputs. If I were to sum that, it's 1. So that's the output of our softmax function. And torch has this max function here. So let me say torch max, and I'm passing outputs.data. Let's see what that returns. Yep, and I guess I'm just getting, yeah, and I'm doing this right here when I do this max for an input. Apparently I can pass, yeah, I'm just passing this extra dimension, it looks like here, that dimension that I'm passing says, okay, well, that's the dimension I want to get the maximum across. So if we look at outputs data, right, the shape of this thing, 16 by 10. So in this case, I guess I was using, was I using a batch size of 16 when I did the test loader? Have to go back and look. Right, but if we just do that torch max, it's going to take the maximum of that entire array. All right, but the same thing like a polars or a pandas data frame or a NumPy can pass it a dimension. So I'm going to say essentially axis 1. So this is giving me the maximum. If I look at those values, let's see. This is actually, let's look at the length of this thing. It's a little weird. It's giving me back 2 objects. So I'm going to say I want to throw away that first one, and these are going to be my predicted outputs. All right, so predicted is going to be a tensor of length 16. So that's the predictions for that batch. Let me just go up and look. I'm questioning myself now. I think I'd said 32 earlier. Let's see. So I'm using batch size of, oh, that's the last batch. That's why. So no, we are using a batch size of 32. It's just as it's iterating over that data set, because of the number of rows that it has, that final batch won't have 32 in it because 32 didn't go into that equally. So that last batch only had 16. That's what it's doing. All right, very good. So all I'm doing is iterating for each batch, getting the predictions, updating the number of total things that I've seen, and then I'm looking at the labels and saying, hey, did the thing we predict equal our labels, and just summing that up. So that's how I'm getting that accuracy. All right, so that's how you would do it if you were wanting to do it, at a batch level. All right, let's look at how we would do it if we wanted to do it on an entire data set. So I've got X-test here. All right, so we want to compute the accuracy on this entire data set. Well, we would want to convert that to a tensor. So we say torch.tensor. Right, and this is a NumPy array, by default NumPy arrays, and we could even check that, right? So remember X-test, if I do the D type, that's a 32-bit. It's not going to like that. If we just hand that off and pass that through our model, that's going to blow up. So what we want to do is we want to say as type np.float 32. All right. So now that's going to be a tensor, and we can look at our D type. That's going to be a 32-bit tensor. All right, so I'm going to say this is going to be our features. So our feature tensor. All right, so in this case, we're doing it for our entire data set in one go. All right, so all 10,000 in our testing data set. And then all we need to do is run that through our model. And we could say, well, outputs is equal to. Right, and of course you could wrap it in that torch no grad thing if you want to be super, because see right here, it's got this gradient function, right? So softmax backwards, right? So I'm just going to run that again, get that model back in. And now when I do with torch no grad, right, I'm going to print outputs, see what that does. So remember, this was previously we ran that without that torch no grad. We got that softmax backward. Right now we lose that. So it's saying, hey, I'm not keeping track of those gradients. And we could also do model eval right in front of that. All right. All right, so we've got our outputs, and then what we want to do, so our outputs looks like this. All right, so this is, again, our, the softmax outputs. If I were to do a sum, let's see, it gives me a dim. So dim is similar to axis. So if I want to sum across the rows, across the columns, right? So for each row, I'm going to sum it across all the values in that row. So dim 1, they're all equal to 1. So that's our softmax output. All right, and we can actually get our argmax dimension equal to 1. Let's see if that, right, so that is going to be our predictions. I think it actually, let's see. Let's see if it takes axis as well. Perfect, so they've made it where it could be nice and compatible with NumPy. So we keep it as dim. If I want to convert that right now, that's a tensor. If I want to make that a NumPy array, you can just do to NumPy, because one thing that we didn't do is we didn't put this on the GPU. So this data and the model are on our CPU. So we can just immediately do this to NumPy. And this is going to be our predictions. All right, and this is basically the same code or the same format that we had when we were using NumPy. We want to look at that performance on our, the performance by digit and the misclassification. So I'm getting the predictions, the outputs, and then I can pass those off, create a data frame that looks at that. And we can see where it performed better. All right, so 0 and 1, it does very good. 2s and 3s, 8s, 5s, that's where it maybe struggles a little bit. And then this is where our misclassifications occur. But overall, it does very good, right? So, you know, 3s are always a little bit of a problem. We think those are 8s, and we think those are 2s, and we think those are 5s. But overall, it does fairly well. All right, so that is it for this video. So hopefully you have a little bit of a better understanding of, you know, the steps of defining a PyTorch model. Overall, you know, there's a little bit of, you know, it's a little bit tedious if you're not used to it, because, you know, you have to use the classes. If you use classes a lot in your Python code, this should be relatively straightforward. But I know personally, and for a lot of people working in kind of, you know, analytics, data science workflows, we're, you know, doing a lot of stuff with arrays or maybe scikit-learn. We don't really have to use classes or define our own classes. We're using classes whether we define them ourselves or not, because when you import like a random forest classifier from scikit-learn, well, it's an object, it's a class. So yeah, we've got to define, in this case, we use that data loader. So we had to make our dataset class, right? So the key thing, we had to have a length and a get item attribute or method, so that it could figure out how long your data set is and how to get specific data elements. And then we could use that data loaders. That helps us batch things up. And then this, we'd have to use a separate class for defining our module. And remember this super thing, that's one thing that's a little bit odd. We run that super init, and that essentially calls the init method of that parent class. All right, so hopefully you found this useful. There'll be some additional videos up in the future, but for now, that is it on a basic PyTorch implementation of a simple feed-forward network for digit classification.